Hey, good morning, chemistry students and my afternoon students. Good afternoon. We're going to be going over the first of the notes in for Unit 3, Chemical Reactions. And for chemical reactions, we're going to be talking today about how to balance the chemical equations, the reactions, and then the 5 different types of reactions. Now, in my notes today, I don't want this recording to last a really super long time, so at various times, especially if I'm doing this on a day with a sub, for my substitute, at certain times I'll ask you to pause it, and on the doc cam, don't push the pause button. You want to push the enter button. The enter button will momentarily pause it. If you hit the pause button, it'll stop and you got to re-go. So anyway, to get going on this, now the first part, everybody's a review, so you don't have to write this all down. We've just been finishing up. We'll be testing soon on our types of bonds. Okay, and so we've got metal to metal or metallic bonds, metal to nonmetal ionic, and then we've done that when you have nonmetals and nonmetals are covalent. And really the big thing here is you've got an electron flying over to that side in this type of a bond. Over here, you've got electrons that are being shared, tends to be pairs of them being shared. And then with metallic bond, it's kind of like a covalent bond, except those electrons can be shared with just about any atom that's fairly close. They don't have to just share back and forth between two atoms. They can share with the whole thing, with the whole chunk of metal potentially, and that's why metals are really good conductors of electricity. But we're not doing that today. Okay, so the difference between these two, this one is ionized and it's a sodium ion. Just a reminder in this unit that when we draw H, that means it's the element hydrogen. If we draw H+, that means it is ionized. It has lost its electron because it would like to think that it's, like helium. And then over here, and we'll be working in this unit with some isotopes again, that when we draw H with the 3 up top, that means it's hydrogen 3. It's an isotope, okay? And when we look at the diagram, since it's hydrogen 3, that's its mass number, tells us there's 3 particles in the nucleus, and 2 of those particles will be neutrons. Anyway, let's go over here. So I think we're getting ready. Oh, okay, here we go. Isn't that funny? That's assault with a deadly weapon. Okay, ha 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 ha. First off, now we're starting our notes. Part A under reactions, we'll call this conservation of matter. So, Part A, conservation of matter. And in a moment, I'll have the we'll pause this and you can get them all written down if you need to. First off, you can't create or destroy matter. That's number 1 under this. Can't do it. They thought you could for a while, but you cannot create or destroy it. Now, you can convert it from one form to another. You don't have to write this. That famous equation of Einstein, E equals mc squared, just means matter can be converted to energy. That's what happens like nuclear fusion, nuclear reactions, but you can't create or destroy atoms. A lot of times they thought when you'd burn wood in the old days, you'd be destroying matter. No, they weren't accounting that some of the particles were turning into water vapor and floating off, and all of a sudden you'd have this big, huge, heavy log that turns into almost nothing. But with Anton Lavoisier figured out, no, if you have a closed reaction system, all the weight stays there. Now, matter can be rearranged, so it is possible to rearrange it. And that happens all the time. The wood gets rearranged into water molecules, a little bit of soot, carbon material. Some of it does. A very small amount of, when you burn wood, a little bit of that matter is converted to energy. That's what we're feeling as the heat. Very small amount. Not enough that you or I can measure. Lastly, oh, sorry, that's tilted. In a chemical reaction, you end up with the same atoms you started with, but they can be different molecules. Now, here's the thing. However, whatever number of atoms you start with in a reaction, you're going to end with those same atoms there. They'll be rearranged potentially into different molecules. Now at this point, push the enter button on my doc cam, and we can pause this for a moment until everybody's ready to go on. All right? And welcome back here now. So, continue on after this. So, Anton Lavoisier figured out you can't create or destroy. Conservation means you save something. Now, let's see. What's my next page here? Now, I'm not going to have you do all that. Now, you can put part B, writing chemical equations, but don't you dare start writing all of that because chemists are lazy. So, part B, writing chemical equations. Now I'll read this to you. So, two hydrogen gas molecules mixed with an oxygen gas molecule, then exposed to heat energy, will chemically rearrange to form two molecules of the chemical water. Now, don't write that because chemists are lazy, okay? They don't want to do that. So let's use chemical equations. Okay, now I'm going to adjust this here. So, let's rewrite that as this, okay? I said we got H2, and we said it was a gas, so we can put a gas, or sometimes you can just put a G after it. In fact, sometimes they'll even put a little arrow up that means, hey, it's a gas. Plus, we're reacting it with oxygen is what I said in there. So we're going to do H2 plus O2. Leave some room in here. Notice I've left some room here. Don't be too quick here. All right? And that's going to change into H2O liquid. So, I might have gone through that fairly fast. So, I'll go back over here, and if you need to pause it for a second. So, first part was we had writing chemical equations, and then that's what we just wrote the equation to all in words. So if you need to pause for a moment, pause, but don't write all that down. And then that we rearranged into this. Okay. Now the problem here is when we just said, whatever the number of atoms we start with, we have to end with. So we're going to start the first part of balancing the equation here. Now this tells us we have two hydrogens. In fact, if you don't have to do this, but there's two hydrogens bonded together. Here is two oxygens bonded together here. They're sharing right there. They're making a bond. Oh, wait a minute. Wait. Sorry. I did that too hasty. Now, you don't have to draw these, okay, everybody? I'm just doing this. So we got the bond going in between there because they're sharing two pairs of electrons there. And this is going to change into water. Okay, I'm going to, I'll just put a little O inside of here so we know that's going to be the oxygens. And so we end up with oxygen over here, and then I'll do a different color. Then we have our hydrogen over here, hydrogen sharing those, and another hydrogen there. Oh, and let me put the dot there. Anyway, okay, you don't have to draw this out, okay? I'm just visualizing it here for you. So, oh, wait a minute, now we got a problem, you may be saying. Okay, here's two hydrogens. There's two hydrogens, okay? We have two oxygens here. Uh-oh, we only have one oxygen over here. Now, the rule for balancing equations is that when we balance chemical equations here, we cannot ever, never change the subscripts. Okay, water is always H2O. What we can do is, though, we can change the number of those in order to balance everything out. So what we can do is, over here, since we need two oxygens, because here's the problem, is our oxygens. We have two over here in what we call the reactants, and we only have one over here in the products. So what we need is, we'll put a coefficient 2 in front of here. Now if you want to put parentheses around there, we got two water molecules. So now, let me redraw that. There's our oxygen, our other new oxygen. There's our hydrogen. Okay, cool. Now we've got two oxygens over here, and we've got two oxygens there. But wait a minute, hold on. Okay, now we got too many hydrogens. Sacre bleu, this is outrage, as they would say in France. So we got two hydrogens and two hydrogens. Oh, okay. So what that means is we got to come over here. We need more hydrogens here. Now you can't say H4 because that doesn't exist. But we can say we need 2 times 2 will be 4 total hydrogens, which means now I think we got this balance. So let's check. We've got 1, 2, 3, 4 hydrogens. 2 times 2 is 4 hydrogens. We've got, okay, I'll put a coefficient 1, but you know how we never put over here the subscript 1? You don't have to put the coefficient. This is called a coefficient, a multiplier 1. But I'll put it there just as we're working through these. So we got 1 O2, which means there's 2 atoms of oxygen in this molecule. Over here we have 2 molecules of water. Each of those has 2 hydrogens and an oxygen. All right, we can now be happy because we have a balanced chemical equation. And that's what we mean when we say balance the equation. Make sure the number of hydrogens in the reactants is the same as the number of hydrogens in the products. And in my actual full-blown notes, there I actually drew the pictures there, but we already drew those. Okay, moving on. Now, we've got this reaction written. I'd recommend let's rewrite it down below, just clean it up. 2 H2s plus 1 O2 changes into 2 H2Os, because we're going to add some stuff to this. And if you drew pictures underneath, oh, sorry about that. Just rewriting the equation there, just to get us ready for up here. So this is number 1, coefficients and subscripts now. So we're under part B, writing chemical equations. This is now number 1 after our little intro there. Coefficient and subscripts. If you need to pause for a moment to get the title written, please do, just for a moment, because then I'll start explaining this. So go ahead if you need to. Remember the enter button to pause the camera. So we've got our equation that we just previously balanced. So the coefficient that I've labeled here, this is a multiplier. Down here, the subscript below the writing, that tells us how many hydrogens there are in that molecule, and the coefficient tells us how many water molecules there are altogether. And let's go ahead, when we're doing that, get that labeled. We're going to get that this side of the chemical equation, these are the reactants, so we got it labeled there. The arrow means a chemical change is occurring, rearranging of molecules, energy, and usually energy is either being gained or lost. And then we're going to get the products. So again, at this point, if you need to, again, to pause that, check with, make sure we got it there, hit the enter button to pause. And we just want to make sure we have the right terminology, because from now on, reactants, which makes sense, they're reacting. Products, these are produced. And I'll talk with you all later. There's some more stuff I don't want to go over today. There's just kind of some rules. So I'd say leave some space today. Okay, when you're working on my stuff, leave some space underneath here, because I'm going to go into a little more detail with this, but not today. And Roman numeral 2 on here. Actually, you know what? Yeah, we don't need to do that part. I think we're just going to, for now, everybody, maybe leave some room, you know, maybe go to a next blank page to get the next part here. Well, actually, no. Let's go ahead and write this one out. Let's write this equation. This is magnesium plus O2 changes into 2 magnesium oxides. Okay, and again, so we use the multiplier here, because when we first do the equation, when we first say that, let me get rid of those for a moment. We say magnesium and oxygen react to make magnesium oxide. Then you'd have to go through and balance it. And we see over here in the process, okay, we got 2 oxygens, we only have 1 there, so now we'd have to put a coefficient 2 over here. And since we have a coefficient 2, remember that means everything in there is going to be 2 of them, so we'd have to have 2 atoms of magnesium to start this reaction. So there was just an example there. And let me see here, do I have another example I'm going to have you do? Yeah. Let's do this example right here. Let's write, and you'll get to do this, I'll let you generate. Let's do H2 gas, and you don't need to write the gas for now, but H2, I'll write it out. H2 plus O2 will change into H2O. This is what happens when they use fuel cell cars, when a lot of rockets, they'll burn liquid hydrogen, liquid oxygen. Anyway, let's start the process of balancing these. What I always like to do, I usually start right here. I have 2 hydrogens. Okay, now let me go over here to the products. Okay, 2 hydrogens. So far, we're okay on hydrogens. We've got 2 oxygens. Okay, we only have 1 oxygen here. And you are never allowed to put a subscript there. No, don't do this, because now this is hydrogen peroxide and it's not water. You may never change the subscripts down there. You can, however, say that you need 2 water molecules because we need the 2 oxygens. So at this point we have 2 oxygens in the reactants. We have 1 times 2 oxygens over here. Now we've changed this equation. Now we got 4 hydrogens, and we only had 2 over here. So let's go ahead and put the coefficient 2 right there, which means we have 2 times 2 hydrogen atoms, 2 times 2 hydrogen atoms. And we could if we want, put a coefficient 1 in front of the O2. You don't need to. Let me make that look more like a 1. There we go. But you don't really need to, because there's 2 atoms of oxygen. 1 times 2 atoms of oxygen, 2 times 1. Okay, this is now balanced. Now what I'm going to do is I'm going to set this over here for you. I'd like to have you, we'll call this little a, little b, little c, little d, little e. So this might be a time for my substitute to hit the enter button to pause, give everybody a chance to get those. In fact, so we don't freak out too much, let's do this. Let's get the first 3 done, okay? So, oh no, that's dumb. Get those all written down, start balancing, and there's a big rule. When you balance these, use a pencil. Okay. Pause and, oh, let me scoot over, sorry. Left off the H2 over there. That would be a bummer. Oh, zoom out like this. All right. Okay, everybody. Oh, yeah, come on, zoom out. There we go. So, hit the enter button, get those written down, and then give the students a few minutes to work on balancing those. And my recommendation is start here, see if it balances, then do the next one, see if these balance, and start doing. Okay. Well, I think you're probably, let's go through and work these out now. So I'm going to work those out for you. And you know what? I almost grabbed a pen. Don't do it, because usually with balancing equations, you're going to have to erase stuff. So I'm going to go through these kind of quick, but here we go. I have 1 zinc so far, 1 zinc. 2 oxygens, only 1 oxygen. So I need to put the multiplier 2. I'm just going to put parentheses. So now I have 2 oxygens in these 2 molecules of zinc oxide. But now I've doubled the zincs, so I need to put over here. All right. And of course, you all know why ship captains don't like the metal zinc, because they don't want their ships to zinc. Anyway, moving on. We have hydrogen iodide. Oh, by the way, let me back up over here. We're going to find out this type of reaction is called a synthesis reaction, because you're taking adding 2 things together to synthesize something new. This particular reaction, you've got a compound here. It's going to break apart into smaller things. They call that decomposition. Anyway, hydrogen iodide changes into 2 H2s and, changes into 1 molecule of hydrogen gas and 1 molecule of iodine gas. Well, we got a problem here right away, because we got 2 hydrogens, only 1 hydrogen. So I need to put a coefficient 2 here. So now I have 2 hydrogen iodines, which means I got 2 atoms of hydrogen, 2 hydrogens. Excellent. Now I have 2 atoms of iodine in these 2 molecules. And oh, look at over here. So we're basically done. For our practice, I'll go and put a coefficient 1 in front. We don't really need to. So that is now balanced. We have 2 atoms over here. Excuse me, take it back. We have 4 atoms over here, and we have 4 atoms over there, because we have 2 hydrogen iodides. And if it helps you in counting, if it helps you to put a subscript 1 underneath those to say, okay, we got 1 times 2 hydrogens, 1 times 2 iodines, total of 4 atoms, 2 times 1 plus 2 times 1 is 4. Because you want to make sure the atoms over here equal the atoms there. All right, so we got boron changing into, and fluoride changing into boron trifluoride. Well, right here now, look at here. Now we're going to have to do the least common multiplier thing. Because when we start off, we got 1 boron, 1 boron. We're good. But we have 2 fluorines here, and we have 3 there. So what you have to do is, when you work that out, you got to find what's the least common, what's the smallest number that goes into 2 and 3 evenly, and that's going to be 6. So what we have to do is, we have to make it now so that we have 6 of these, and that we end up over here with 6 over there. So if I make this 3 difluorides over here, changing into 2 boron trifluorides, I'm going to put parentheses around. 2 times 3 is 6 fluorines. 3 times 2 is 6 fluorines. Good. Over here now we have 2 borons. Okay, and over here, oh, okay, we got to then do this. We are now balanced. 2 borons, 2 borons. 6 fluorines, 6 fluorines. Over here, nitrogen gas plus hydrogen gas will form ammonia. And let's see. Well, right away we can see nitrogen, we have 2 over here, so we'd need to have at least 2 over there. Now this is where pencils come in, because we may have to erase this later. So we got 2 nitrogens. Now let's see what happens. Because we have the coefficient 2, that means we have 2 times 3 is going to be 6 hydrogens. Well, we only have 2 over here, so okay, 2 times what is going to be 6? 2 times 3. So now, let's see now. 2 nitrogens, 2 nitrogens. 6 hydrogens, 2 times 3 is 6 hydrogens. Okay, we got it. And here we go. Iron plus water changes into rust plus some bubbles of hydrogen. So we can see right away, okay, like I said, I was like, sorry, we got 1 iron here, we have 3 over there. So we know immediately, okay, we're at least going to have to put 3 here. So now, let's come on over here. We got, let's see, H2, we got 2 hydrogens, we got 2 hydrogens. Well, we don't have to mess with that yet. But, look at here, we have 4 oxygens, okay? So that means we got to have, we only can get oxygen from the water here, so we got to have 4 of those. So now, let's see, that means we have 4 oxygens and 4 oxygens, 3 irons and 3 irons. Oh, this, okay, but now we have 4 times 2 is 8 hydrogens. Well, look at here, that's real easy. 2 times 4 will be 8 hydrogens. So I think we got this balanced. Let me double check. 3 irons, check. We've got 4 times 2 is 8 hydrogens. And we got 4 times 2 is 8 hydrogens, check. We got 4 times, remember there's that invisible one there. We know 4 times 1 oxygens is 4 oxygens. And we have, if you like, we can put the coefficient 1 times 4. Okay, this is now balanced. Okay, so there you go. And let's see what the next thing is here. The next part is we're going to do part C, types of chemical reactions. Types of chemical reactions. So I'm going to get right into that. And the first type, part 1. And again, I'm going to go through this fast in my notes here. You may have the sub hit the enter button to pause it for a moment as we go through these. Okay, so why don't you go ahead, pause it for a moment, let them write it down, and then I'll talk about it. All right, so I'm back here. I'm using some symbols here. So you've got one compound. This can be, whatever compound R and compound S. In a synthesis, they're going to combine together. Now, this represents that they're either ionically or covalently bonded. Okay, we don't care there, but the thing is that they're bonded together. This is synthesized because that means to create, to make. Now, the next type of reaction, okay, and I like this analogy. You go to a dance. Here you are by yourself, and you see this guy or girl over there, and you say, hey, you want to dance? And next thing you know, you are now bonded together in dancedness, okay? So, coming over here, decomposition. So now, let's have you, okay, why don't you go ahead, let's get this written out. Again, hit the enter button on my .cam to pause it for a moment, and in a moment I'll talk about this. All right, so what we got here, so decomposition, you've got a compound that is together. It could be water, it can be ammonia. It goes through a reaction and it breaks down into the parts that make it up. Now, this is real simplified. We're not worried right now about balancing the equation. We're just worried about showing that in a decomposition, you've got a compound, a molecule together here, and it breaks into smaller parts. With my dancing analogy, you're dancing together, the dance ends, so now you break your danceability bonding thingy, and you end up, now you're by yourself again. So this is decomposition. And, oh, here we go, popping on down to here. Okay, now, at first this seems kind of confusing, but it's not. So, number 3, single replacement. This would be a good time, if you need to hit the pause button. And I'll talk about it in a moment. Okay, hopefully you had time to get this written down. So, with a single replacement, you can see we've got a molecule here, and another atom comes in, and it could potentially even be another molecule possibly, but it's probably, let's say it's another atom. And then what happens is, it's going to switch with one of these. My dance analogy is, here's a couple dancing, and then somebody comes over and says, hey, taps you on the shoulder, I want to cut in. So this is like cutting in on a dance. So you end up now that you get T and S start dancing now, so they form together, and then one of the elements is kicked off, or one of the dance partners goes off. So here we got a single replacement because just one of these dance partners is being replaced. Now you probably figured that the next one is going to be double displacement, and this tends to be happening in ionic compounds. So let me go ahead and have you pause for a moment, give them a chance to write this down. Hit the enter button. All right, so let's talk about double replacement. So what's going to happen is this compound is going to switch with this compound, which would be like the anions that make up each of these compounds. They're going to trade their cations. So the R is going to team up with the U over here, and then the negative S anion is going to team up with this one. So they're switching partners. So this is like you're at the dance, and you're dancing with your partner, and your best buddy is dancing with their partner, and you go, hey, let's switch. And so in the middle of the waltz, you switch partners, and now you're dancing with your best buddy's friend. And be careful, this can cause problems. Anyway, because you can have a really bad, something bad could precipitate from this. Okay, these are precipitation. We'll do that later. Okay, so double replacement. So the compounds both replace. And we've got our last one, my favorite. It's called combustion. Combustion. Oh, let me turn this over so that doesn't. Okay. So I'm going to give you a moment. Go ahead and let's get this written down. Hit the enter button, and I'll talk about this in just a moment. Okay, so here I'm back. So when do we get this written out? With combustion, this is burning, and combustion means a hydrocarbon. A hydrogen with a carbon. That's what they call hydrocarbons, like fuels or hydrocarbons. You hear them talk about the news. Oh, we're dumping, we're using too many hydrocarbons, making the atmosphere get warmer. Now, you have a hydrocarbon reacting with oxygen. Oxygen sucks electrons off of other molecules, okay? So what happens is in a combustion, you have a hydrocarbon reacting with oxygen, and it's going to form carbon dioxide and water. Yay. So if this is wood, it'll mix with oxygen. It's going to form some CO2, and it's going to make some steam. Now, this is assuming we have perfect 100% efficient burning here. What happens a lot with burning wood, you don't get total perfect burning here, and you end up with chunks of carbon, which is like some of the ashes and stuff. And there's a data table on this page, and I'm going to show you the data table here. So these are some terms you may have heard before. Methane, we've talked about. Ethane is not very common, but ethanol, you might hear them talk about making ethanol for fuel for cars. Propane, that's what we use in a lot of times, for camping and stuff. Butane, okay, butane in here. Woohoo, look at there. I'm doing a combustion reaction. Okay, the butane is mixing with the oxygen around here. It's making carbon dioxide. We can't see it, and it's making some oxygen that we can't see. So, 100 years ago or 200 years ago, people would have said, oh, look at, the fuel is changing into nothing. Well, hey, it is changing into something. So, there you have it. There are these reactions, and there's a little trick for balancing these that I'll show you later. And I think at this time, everybody, I'm glad you got the notes all done here. And what I'm going to have you do is I'll have the substitute handout. I'm thinking, to begin with, the first part is I'd like you to get this paper here. This is the writing balanced equations. Now, this is a step-by-step process. So when you're working through this paper, okay, these are each the steps showing you how to go through and balance these. Now let me zoom out so you can actually see it. Then there's questions on the back for you to work on these. So I'm going to give you about maybe 10 minutes to work on these together. But again, the idea here is, here's our equation. This is the unbalanced equation. We've got C3H8. Wait a minute. C3H8. Oh my goodness, where did I just put my chart here? There it is. C3H8 is going to be propane. So in this example, we're burning propane. This is a combustion reaction. So this is the base equation here, and it's going to show you here how many carbons, how many oxygens. Then it's going to go through step by step, like I was showing you before, a process for balancing those. So here's the next step, okay? And it's like, oh, look at here. I can see right away we got more CO2s over here. And then the next step, as I look at it, I'm thinking, oh, wait, look, we got more waters over here. I can see that right away. And then the next step here, it's like, oh, look, we've added more oxygens here. So about 10 minutes, work on this. And then I've got another worksheet for you. Thank you. Oh, okay. Pause for a moment. Okay, the next worksheet that you'll be working on is this balancing equations challenge. Okay, let me get this off of there so you don't have to see that. So I'll have the sub hand this out to you. And oh, by the way, I'll have a key here so you can check, and see if you did it right. But just go through, fill these out. Okay, label the coefficients, the subscripts, all that kind of stuff. It's just like from our notes. Then on the back side, we got a bunch of problems for you to practice. And then we'll have you practice those problems. And then we'll have you watch a video. And then there you go. Bye. A note to my sub. I do have a copy of one of these, a key all filled out for you. So if you want to, you can show it on the doc cam and go over it with them when they're done. But don't you dare do that unless they've actually done it, okay? All right, thank you, and I'm stopping this video now.